All right, hello, welcome. We're glad you're here. It's a beautiful day outside, so I appreciate that you chose to stay inside a little bit, but we get the sun through the windows. So, very glad that you guys are here. Hope you've had pizza. If not, be sure and go check over there. But we are here today for our last STEM So What of the semester, and it's on quantum computing. So I am very excited about this, and I'm sure you are too, and that's why you're here. So that's great. I do want to make sure that you know a couple things that are coming up. I guess that's 2 weeks, is Earth Day and all the Earth Day activities. So there'll be a Fun Fest on Thursday, April 24th, disc golf on April 25th, and then a 5K run. I know you're all dying to sign up for that. 5K run on Saturday the 26th at 9 in the morning. So be sure and join us for that. One other thing with Earth Day, they were trying to tell you over there, but if you didn't see it, we have raffle tickets. They are $5, and they are to win a rain barrel. So the Marine Creek Land Scholars are doing this. It helps pay for scholarships, and you have a chance to win one of 2 rain barrels. So these are here. If you want one afterwards, you can come down to where all the tables are and give us $5, and then you can grab one. And that'll put you in the contest to win one of 2 rain barrels. Okay? And then, because I don't know how well you can see these TVs, depending on where you're sitting, we do have lib guides. We have lib guides, and the lib guide has the actual PowerPoint for tonight. So if you want to follow along on your phone, especially those of you who are sitting up on the stairs, just go ahead and scan that QR code. You'll be able to bring up the PowerPoint and follow along with the speaker. Those of you who made the choice to sit down here close, good thinking. But if you want it on your phone, you can do that too, right? Also, when you go to that lib guide, you will see we have all the previous STEM So What events there. So if you want to watch a video from one of the past events, or there's all kinds of extra information about that topic on there. So it's a wealth of information. Be sure and check that out. And speaking of a wealth of information, if you haven't done it yet, Phil, the librarian, is over here with some books and other online resources related to quantum computing. So make sure you check that out before you leave. And then I'm going to invite Catalina up. Catalina Boudreau teaches physics here, and she is the one who made sure we had a wonderful speaker. So I'm going to let her introduce him.
Hello. And yes, we have the greatest speaker that we can have tonight for our last event of STEM So What. He is Dr. Gordon Brown. He grew up in Coppell and went to high school in Coppell. He received his PhD in mathematics from University of Oklahoma in 2017, but didn't even know that it was possible to major in math until midway through his freshman year of college. He had never heard of quantum computing until 2022, but is now the lead quantum computing researcher for Lockheed Martin's aeronautics business. He has been a judge at many science fairs, including the International Science and Engineering Fair. He lives in Benbrook with his wife Emily and has 2 sons, Andrew and James, and enjoys going to trips with them to exotic faraway places like Denton, Texas. And now we have for us Dr. Gordon Brown.
Thank you. How's everybody doing? Good pizza? Good enough? Thank you so much for having me, Jennifer, and for inviting me, Professor Boudreau. So, I am going to talk about quantum computing. But first, I want to ask you a question. Have you ever had somebody in your life who saw something in you before you saw it in yourself? So you can think about that while I keep talking. I did. My grandpa, Bill Brown, he was a lifelong learner, and the character trait that he prized most in other people was enthusiasm. And one day, he asked me, "Gordon, do you know anything about quantum entanglement?" I was in high school. I said, "No, I don't." He said, "Great." And the next day, he gave me some papers stapled together. It was a research article on quantum entanglement. And it was clear from the way it had been folded and creased and written on that he had been reading it before me. And you see, his personality with his love and enthusiasm and learning was such that he didn't even go by grandpa. He had asked us from an early age, the grandkids, to call him Uncle Billy. Made him feel younger. Uncle Billy was what we called him. And Uncle Billy had written at the top of the first page of this article that he gave me in high school, "Gordon, have fun!" exclamation point, Uncle Billy. So why was he giving this to me, and why was he reading it himself? Well, I read it, and it was really hard. I had to look up every other word multiple times. I had to stop and start again, come back a few months later, and read the same paragraph again for the 10th time. But he was right. I did have fun. How did he know? So I would like to think that Uncle Billy didn't just see in me intellectual ability, but hopefully some of the curiosity and tenacity that he most cared about in life. And so as I conclude that story and move to the main topic of quantum computing, I give you permission, audience, to use a percentage of your brain power to think about that question in your mind as I talk. Was there ever somebody in your life who saw something in you before you saw it in yourself? Quantum computing. You may have seen news articles over the last few years. If you want to Google that right now, you will. There's some powerful new computing paradigm. It's going to revolutionize computing. And you may have seen pictures like that. That's an IBM superconducting quantum computer. And we're in a really interesting time right now. We're like in the 1950s for digital computers. These things will be very powerful on very specific problems, but they're in the really early stages of development. They take up the size of a small bathroom. Nobody owns one yet, except megacorps like IBM who are building them, right? And they're insanely expensive to run. What you see there, that upside down wedding cake shaped thing that looks like it's made out of brass or something with all the tubes, that's not the quantum computer. That is a glorified refrigeration device. These things have to be kept really cold. Now, like I said, they will be powerful on certain specific problems. You're never going to scroll through TikTok on a quantum computer, I promise you. That's overkill. Your phone is perfect for that. But if you want to model the behavior of plasma inside a fusion reactor, you might need one of those. But like I said, they're extremely sensitive quantum mechanical devices And so right now, they're prone to errors left and right. They're so sensitive that a stray electron can cause them to not give you the right answer anymore. So the main problem in quantum computing is, with a close second being making them and scaling up, is correcting the errors on the fly. Your computer already does that. It's called error correction. So I have 20 minutes to tell you about quantum computing. That's not a lot of time. I had to pick one thing I really wanted to tell you about, to get across to you. And I am a mathematician, by the way. So Professor Boudreau, I don't know if she knew that. She said, could you give a physics talk? We need a physicist. I said, I have a PhD in mathematics, but I know one physics thing. So we are going to do some math, but just breathe, okay? I don't expect you to understand all the symbols I'm going to put up there and all the things I'm going to say. I just wanted to wash over you so you'll walk away with this one lesson from me, I hope, which is, why are quantum computers different? Why did they get their own name? What is so special? I'm going to show you one example to try to explain that. Okay. I do have to give a little bit of background first. So if I'm going to explain what a quantum computer is and does, I need to go back to your computers. They're called classical computers. Classical is a word you are now free to use and sound cool saying. That means not quantum. So all the computers you've ever used in your life are classical computers. How do they work? Well, that's its own talk, but if you gave me one slide, I would say it has a processor, and that processor runs circuits. This is basically a function that takes in a string of bits, zeros and ones, applies some operations to them. They're called logic gates, all those little symbols in the middle there of all the wires. And you get some bits at the end of it. That's a circuit. Your processor can run gazillions of those per second, and that's why you don't have to worry about it. So every piece of software you have ever interacted with, and you might be interacting with right now, is just an interface between you and a CPU that is running circuits really fast. Okay. Let's start going down the rabbit hole. The basic unit of information in quantum is not the bit. It's the qubit, quantum bit. And the people who came up with the term qubit were trying to be funny, so you can laugh. It is not 0 and it is not 1. It is both and neither and somewhere in between. That is the first of at least 4 things I will say in my talk that should sound to you completely crazy and nonsensical. It is a quantum system which is in a superposition of 0 and 1. So I've got the first math notation up there. I've got some symbols that are inside this ket notation. It's called ket, K-E-T. That's that bar and that angle bracket. And for all you care, that just means we're talking quantum. You could delete those in your mind if you wanted to. On the left, we've got a psi Greek letter symbol. That's our qubit. On the right, we've got a 0 ket, a 1 ket, and some Greek letters in front of them, alpha and beta I picked. Those are complex numbers, the alpha and beta. Yes, you heard me, you cannot do quantum computing without complex numbers. Thought they were useless? They were until now. I kid, of course. I love complex numbers. What does a quantum computer do? Roughly speaking, it runs quantum circuits. It takes in a bunch of qubits, each in a different superposition of 0 and 1. It applies some operations to them. They're called quantum gates. And you get some qubits out at the end. But the rabbit hole goes much deeper. That's the same circuit as on the last page, just over there. We're not going to talk about it too much. I just wanted to show that you can draw these in a similar way to a classical circuit. Qubits, having them at the end of a circuit is actually useless. They are stuck inside the black box that is the quantum computer. To actually get some use out of the circuit that you just ran, to know, did I get the right answer or not, you need to open up the black box, so to speak. You need to observe the qubits. But as Professor Boudreau will tell you, observing a quantum system changes the system. So I kid you not, when you use a quantum computer to do what's called measurement, measure each qubit, it will collapse into a bit and either suddenly be 0 or 1. That's the second crazy nonsensical thing of the evening. What do you mean collapse, Gordon? I'm off the hook for that one. No one knows what is meant by the collapse of the wave function. That's a hotly debated topic in physics to this day, and we don't have time to go into parallel universes. But yes, they somehow know they're being observed, and they can't be quantum and be observed at the same time, so they'll go back to being classical. So really every quantum circuit is start with qubits, apply some quantum gates that you want to apply, end up with qubits, and then measure each one. Get bits at the end. Then you're done. Remember those alpha and beta that were in front of the 0 ket and the 1 ket, those complex numbers? Rabbit hole gets deeper. Those are called amplitudes. We needed a special name for them. They determine how likely it is that your qubit, when it's measured, is going to collapse to 0 or 1. You heard me. How likely? Meaning, quantum computers are not deterministic. They're probabilistic. That's the third crazy thing. What I'm saying to you, to be crystal clear, is if you take 2 quantum circuits, the same one 2 times, same quantum circuit, same gates, and start it out with the same qubits and run it 2 separate times, same inputs, same function, you could get different outputs, different bit strings. Okay, so you should be wondering now, if you're sane and you're following what I'm saying, how is that useful? How would it be useful to have a computer, same function, same inputs, different outputs? That's useless. Well, what we're going to do is we're going to take advantage of the probabilistic nature, and we're going to run our circuit that we've chosen many, many times, like 1,000 times, really fast, each time with the same starting qubits. And so we end up with 1,000 bit strings, and we build a probability distribution over the bit strings. And if we work it right, the bit string that is the correct answer to our problem that we're trying to solve will be like the mean or the mode of that distribution. We can analyze the probability. Are you still with me? Is this cool? I hope so. Sounds useless still, probably. So what's this example I want to walk you through where I'm going to put up some math, but I just want you to understand a little bit, like, why are they different, quantum computers? So I picked this out. I made this up myself. This is a Gordon special. It's an exclusive. Say you have a friend. You say, don't pick a card, but just think of a card in your mind from a standard deck of 52 playing cards. Just think of it. Don't tell me what it is. They've just got it in their mind. We want to figure out what card they picked. If we are not mind readers and we don't have a quantum computer, all we can do is guess and check, trial and error. Is this your card? Nope. Is this your card? Nope. And so on. That's called brute force unstructured search, is the fancy term, right? In the worst case, we might have to ask all 52 times. It might be the last card we guess, right? how could a quantum computer possibly improve on that? Let's see. First, we're going to encode the cards as bits of strings of bits. That's just the language that computers speak, is bits. They don't understand ace of spades, two of clubs. So now every card is a bunch of bits, and whenever we want to go back to, wait, what card is that bit, or that bit string? We can't. Right? In our quantum computer, we're going to create a quantum state which is a superposition of all the cards simultaneously. The way you do that is you start with 6 qubits. It's 6 qubits for the same reason that you need 6 bits to represent 52 cards. They're all in the 0 state when we start out. They're not really in a superposition. They're sort of 100% likely to collapse to 0 if you were to measure them. That's what that means with a 0 and a ket. There's no other alpha and beta. It's just alpha equals 1. And that's how quantum algorithms usually start. And the way you create a superposition is by using on each qubit individually this quantum gate. It's called the Hadamard gate. It's the best friend of every quantum algorithm scientist. And so it changes each 0 ket into a little superposition like we saw earlier. It's got a plus, and it's got the 0 and the 1. And a scalar pops out, and it's 1/8. Don't worry about that. You can ask me about it later if it upsets you, but it's just the scalar that pops out to make this a valid quantum state. And if you wanted, you could multiply that all out and expand the sums, and you would get what's on the lower line there, a sum of all the cards, all the kets. That's an algebraic model of what is happening inside the device physically. One of those kets, one of those cards in that superposition is the winner, W, that your friend picked. I don't know which one, but I know it's one of them in that superposition, right? And I'm going to use that. So how can I increase the amplitude of that W ket, the winning card, and decrease the other amplitudes of the cards I don't want without knowing what W is? I mean, I hope you're intrigued, because I can't make this any more intriguing. Here's what we're going to do. We're going to rewrite our quantum state S as the winning card, W, by itself, plus the rest of the cards. I'm going to call them R for rest. I just bunch them all together. I don't know what W is, the winning card. I'm just saying one of them is W, and I'm at liberty to express it like this. Right? We could make a geometric picture of this situation. It is like we have a 2D plane, the good old XY plane, and the winning card is like this vector at 90 degrees. And the rest of the cards your friend didn't pick, R, is the other axis. And we're somewhere in the middle, our S. This is not to scale. There is some angle theta that makes this work, but don't worry about it. We're somewhere in the middle. We start out much closer to being in line with the rest of the cards than with the winner. And we want to somehow apply quantum gate that will make this picture change so that our superposition S moves up to where W is, and then we'll be ready to measure all the qubits, because with high probability, we'll get the winning card. This is just a picture to help us understand what's physically going on in the machine. The quantum computer is not actually like making angles and arcs, just a picture. Okay, so what quantum gates can we apply? Well, there is a quantum version of asking your friend, is this your card? There's a way to make that into a valid quantum gate. And what happens is you do the equivalent of this. Friend of mine, flip the sign of the winning card in my superposition, I won't look. Flip the sign meaning from plus to minus or minus to plus. They know what the winning card is. They picked it. So in this analogy of the friend magically poking the quantum computer, that's not really what happens. It's a gate. But they could flip the sign on the winning card without telling me what it is. That would change my superposition to something else. It turns out, if you ask, what does that do to the picture? It actually reflects us about the r-axis. We are now farther away from where we wanted to be. We wanted to go up, up, up to the winning card, which is this 90-degree vector. Darn it. But you might be thinking, okay, if that reflection was a valid quantum gate that we're allowed to do, could we do other reflections and get closer to W? Yes. We could reflect about the superposition state S that we started with. That would vault us closer to W. We would now be in the net effect closer than where we started. Stay with me. Now we could do that whole thing again. Okay, friend, I have a new quantum state, a new superposition. Now flip the sign of W in that quantum state. I won't look. Looking would observe the qubits and measure them. We won't want to do that yet. That throws us down where we don't want to be. We reflect about the new superposition we just had on the second iteration. Now we're closer to W. Is this crazy? We are walking through a mathematical model of what's going on at a physical machine. We're applying operations that are the equivalent of the machine moving through some multidimensional space towards the right answer, which it doesn't know. That is the point I am trying to make tonight. A digital computer cannot do that. You can only do that if you have quantum superpositions. Okay, so mathematically, we can keep applying these two gates, and we'll march up towards W in a finite amount of steps. This picture is not to scale. It looks like, oh, we only have like one or two more steps to take. Yes. So you could ask, how many of those iterations will we need to do before we're ready to measure, and we're pretty confident we're going to draw W, their card they picked? The answer is, in the worst case, 8. 8. The time to lose your mind would be now. I think I forgot to say a couple slides ago, but it was written there, that asking your friend in this metaphor to flip the sign of some ket in a superposition, that's called querying a phase oracle. Remember it was written in green? Query is a fancy word for ask. Phase means a complex number like a sign flip. And oracle means your friend who is all-knowing, right? So we can ask, what is the query complexity of this algorithm? How many times do we have to ask the oracle? And it's 8. The query complexity of guess and check, it was 52 in the worst case. So what I'm saying is, in general, this is called Grover's algorithm for unstructured church. Grover is the last name of an Indian-American physicist who came up with this in 1994 or 5. That's a quadratic speedup. If you play the same game, but instead of 52 cards, there are 1 million, guess and check, in the worst case, will take 1 million queries of the phase oracle. Grover's algorithm will take 1,000. A lot better, right? That's the end of the quantum computing spiel. This is the best example I could come up with that really doesn't shy away from a little bit of math, but gives you the point. They're different. It is a different animal than a digital computer. It can do different things you would not normally think of, right? I encourage you, now that you've seen a bewildering display of abstract math to describe what a quantum computer is and does, Google around. There are dozens of, just off the top of my head, great news articles, papers, but also YouTube videos, how we all actually learn in real life, am I right? And I encourage you to study more. I didn't say a word about how do you make a qubit? Like, how does the IBM superconducting quantum computer make a qubit? Like, what does it do physically? I haven't said a word about that. That would be a great other talk. And so, as I wrap up, I do want to return to the original question I asked you. Right now, I bet you there is someone in your life who sees something in you. The question is, what do you see? Thank you.
We do have a few minutes for questions. So if anybody has a question, Jeremy has volunteered to run around and bring a microphone to you, and Dr. Gordon Brown will answer it, hopefully.
Could you touch on geometric quantization? Quantization?
Could I touch on geometric quantization?
Yes.
I have never heard those two words together, so I cannot. Could you touch on geometric quantization?
Probably not in this exact moment. Do you think one day a quantum computing breakthrough could root outside of traditional physics or traditional quantum physics, such as philosophy or neuroscience?
Do I think a quantum computer could have application?
Do you think a quantum computing breakthrough could root from the study of examining neuroscience and philosophy as a quantum system?
I am optimistic. I am not an authority to make grand gestures tonight, but if you're just asking Gordon, citizen of Fort Worth, Texas, not like professional scientist, yes. The kinds of problems that a quantum computer would be good at are the ones that are really high in complexity. And they are in their early stages. They're behind, for example, AI in terms of technological ability, but I think so, is the short answer.
Thank you, Dr. Gordon Brown.
Please. My mother named me Gordon, that's good enough for me.
For students who are interested in this topic or who think this might be something that would have great application in the future, what kinds of things would you recommend they study, or what skill sets would they want to develop in order to participate in making use of quantum technology?
Yes. That's a deeper question than you would think. You'd think I can answer it in 2 seconds, this and this, any other questions? But I want to give it a little background first. So I just said quantum technologies are a little bit behind, for example, artificial intelligence. And I use that example because 10 years ago, I work at Lockheed Martin. 10 years ago, if you wanted to do artificial intelligence, there was no bachelor's degree in AI. There was no job code that you could have at Lockheed, for example, called AI engineer. It was just a smattering of coursework and probably a master's or PhD that you needed, and then you might get lucky, but your job title would be software engineer. That has all changed. You can now get bachelor's degrees in it, get a job in specifically AI, and your job code and title will be AI engineer, and you'll have a higher salary than a vanilla software engineer. So quantum computing, I always say computing. There are other technologies that are quantum that are not just the computers. That's just my thing. To do work in quantum, right now, it's in that earlier phase, where for the most part, there are no quantum engineering bachelor's degrees. And there are some, and more every day, but not that many quantum engineer positions that you'll find when you Google that career path. So I have to give this unsatisfactory answer, which is you need some math and some physics, right? But most importantly, programming. That is still the case. And you're in luck. If you want to program a quantum computer, the standard industry-wide language of choice is Python. So it's a friendly language to learn. I would encourage you, if you are interested, IBM, and probably a couple other companies now too, they have all of their quantum computers hooked up to an online portal. It's called IBM Quantum, that you, a person off the street with an internet connection, can make an account for, and you can learn through their official tutorials how to write Python code to execute quantum circuits on their literal quantum computing hardware, not, well, sort of, kind of, no, real quantum computers. Of course, if you don't have like a premium subscription, you can only run so many circuits per day or whatever, but that is the best way to learn, and that is the best way to answer that question of what do I need to learn while I'm in school to prepare myself. It's a base of programming such as Python, and then it's math such as linear algebra that is the most important, and then any physics you can take is helpful. If you are able to take a quantum mechanics course, that would be ideal, or you can just follow Professor Boudreau around. That's her specialty. She'd love to talk to you about quantum mechanics.
Kind of a follow-up to that then, when you were going to school, I'm assuming there wasn't a lot of quantum classes and things, but you were already interested in this thanks to your grandfather. So kind of, can you tell us more about that path, what you did at school, and how that led to getting to where you are now?
Yeah, I understand the question is basically, how did I get where I am? Yeah. So it was weird. A lot of people, if you ask them, how did you get where they are, it's this weird pinball story, right? Okay. I was interested in a lot of things. I am a STEM nerd, if you haven't been able to tell. That's the real reason I'm here. I'm not a quantum computing expert. First and foremost, I'm a STEM nerd. And I put the M in STEM, thank you very much. But I just was really interested in math, and I did get a bachelor's, master's, and PhD in just pure math. And there's a story about how I got to Lockheed, and that's not really what's being asked here, so I'm going to skip that. But once I was at Lockheed and I was doing mathematician things, I learned about quantum computing just through news articles, like a 60 Minutes episode, something like that. And I thought, that sounds, freaky and interesting as heck. So I just asked around. I had a mentor at Lockheed Martin. I asked him, is there anyone here who does quantum computing? He said, yes. There's one guy. And I contacted him, and he said, here's some money. Go do quantum computing and report back. So I had some doors open to me because of my education and my employer. That is a fact I cannot avoid, and I won't BS you. But again, if I were to do it again today, or if I were to give you advice, it would be start with the IBM online portal. And there are others, but they have tutorials, and you could just learn Python by trying to program a quantum computer with the IBM toolbox. Have I answered your question? I kind of talked around it. That's what we mathematicians do. We love circles. So.
Hello. I wanted to ask, like everything else have a role in our life. Like when we learn cybersecurity or learn about computers, it does play a role in our life. Why do we have to learn quantum? What role does it play in our life? Like it's only for guessing numbers, or it does play any other roles?
Thank you for asking. I have a great example for you. You mentioned cybersecurity. So I will give you a cybersecurity example from quantum that will make you go, oh, I see. Grover's algorithm was the second big breakthrough in the 90s that made people go, oh, quantum computers are not just a crazy idea from Richard Feynman for modeling physics. They could actually do something, and we better start building them. The first breakthrough was another thing. It's called Shor's algorithm. Peter Shor is the man's name. And it is an algorithm that can run in polynomial time on a quantum computer, if you have one, that can factor large numbers into a product of two primes. Who cares, you ask? Well, all of the modern day cryptography, I should say encryption protocols that are protecting all of your banking transactions that you're making on your computer rely on the fact, to guard against cyber attacks, that large numbers are very difficult for digital computers to factor into primes. It's called RSA cryptography, or public key cryptography. So what I'm saying is, it is a well-known fact that when quantum computers come of age and are no longer swamped by errors, that's called fault-tolerant quantum computing, you could run Shor's algorithm and break RSA encryption in, a double-digit number of hours. We will need something better to protect just for example, our online transactions. And you can Google this, it's a thing, PQC, post-quantum cryptography. We will need algorithms that protect against quantum computer cyber attacks. So that is my go-to example. And Shor's algorithm, I gotta go back to the math, I'm sorry, that's my thing. Shor's algorithm packs an even bigger punch than the search algorithm, Grover's search. It makes an exponential speed up. This is a quadratic speed up. So that's what kicked this whole thing off. That's what made people want to build these things.
Hi. In the beginning of your presentation, you did mention something about keeping the quantum computers cold. Why is this?
I am not qualified to answer that question. I actually, preparing this talk, I thought to myself, what if somebody asks about quantum computing hardware? Yes, I do not know, other than in general, there are two kinds of quantum computing paradigms. One's called trapped ion and one's called neutral atom, where in order to make a qubit, you're going to use one atom, either neutral, so no electrical charge, it's got all its electrons, or ionized, trapped ion. And you need to keep it still and in place, so you could apply quantum gates to it without it moving around. That's why you need to keep it cold. That is my, I took physics in high school answer. I'm a mathematician, not a physicist. But that is the basic answer. I really encourage anyone interested in the physics or just the computer engineering of these things, please go learn about it. Do not walk away from this thinking you have to do weird, boring math or, to do quantum computing. There are so many aspects. Thank you for your question.
Thank you.
Hello. So I had a question. In the beginning, you talked about the analogy of finding which card was the correct card, but the way you described it was like on the graph, you're getting closer to finding the answer, but like you're taking steps. But if one answer is correct, all the other cards are wrong, and only one card is correct, how can you be any closer to being correct than just being correct or wrong? I mean, how can you move towards the correct answer when it's one or the other? But a classical computer can't do that, but it seems like maybe in quantum you can be closer without being closer, kind of?
The answer to that question is just as mysterious as the answer to the question, how can you make the very simplest kind of superposition in the first place, a single qubit between 0 and 1, right? How can it be between 0 and 1, and how can you move it with a quantum gate closer to 1 or closer to 0? So that's my unsatisfactory answer to your question, which is if you could wrap your head around the concept of superposition, then I just did it on a larger scale. I had 6 qubits and I made them into this much larger superposition, and I applied quantum gates to all of them at once to move my state to some other state. That's just what you do to one qubit on a larger scale. So it's one of those things. I can explain it, I can't understand it, though.
I like that, though. Very mysterious.
Kind of circling back to your cybersecurity question, how long do you think it'll take until quantum computing can help with the cybersecurity, like encryptions?
Great question. I don't know, and I'm very scared to end up with, my picture under some headline, There will be news articles readily available on a Google search that can tell you more than I know. All I know is it is inevitable. I think it's a single-digit number of years from now. How about that? And what I can say with more confidence is the two main problems are number of qubits, right? That's first one. There's going to be a second one. So right now, you guys are younger than me. Some of you, you might have in the pocket of your jeans right now a 1 terabyte solid state drive, and that's not even eyebrow raising anymore. Okay, the quantum computers we're experimenting with right now, like let's say from IBM, that's the example I keep giving, they might have 7 qubits. Not 7 teraqubits, 7 qubits. I think now they have a quantum processing unit QPU that has maybe like 1,400, but we're not there yet, right? One day we'll talk about teraqubits, but it's not today. The other problem is what I keep harping on, this lack of error correction. being swamped by errors right in the middle of your computation and therefore getting a completely wrong answer and not necessarily realizing it, just showing your friend the card and, oh, that's not your card, darn it. Those are two humongous problems standing in the way of Shor's algorithm being able to factor large numbers into primes on actual quantum hardware. Here's my kicker to your question, and then I'll stop talking, I promise, for a minute. Ask me, what is the largest number that has ever been factored into 2 primes using Shor's algorithm on an actual quantum computer to date? You think it's got to be some ungodly high number, right? Oh, no, it's 21. Which I'm not sure if you're aware, but that is a product of 3 and 7. We got a long way to go. There was a gentleman up front who made a very good point that I would like to repeat into the microphone. The algorithms for protecting against quantum cyber attacks, PQC, post-quantum cryptography, those are already available, right, in mathematical form, and you can implement them on your digital computer to some extent. That's a very healthy, advanced subfield. The subfield of making quantum computers and running them and actually getting good results, that is the big mountain to climb. Well, I would just like to say thank you so much. Oh. Matt has another question, part 2.
Hi. Guess, sorry. So you did mention something about getting 2 wrong answers. If you're sure you don't have the correct answer, then how are you sure that you have the wrong ones?
Kind of a catch-22, isn't it? You aren't. Yes. So you, if your name's Gordon and you're a young, intrepid quantum computing scientist, what you're doing is testing your algorithm that with a small number of cards, to use the card analogy, on your digital computer and guessing and checking, and so you know from that, you have what's called the truth data. I know, because I made up the problem instance, what the right card is and what the wrong ones are, and I'm going to test the quantum computer to see what it comes up with. So that's how you test these things, but then in actuality, when you actually run it for real and try to show your friend the card, yeah, you don't know. You don't know. However, do I need to wrap up, Jennifer? Okay, all right. I would like to add one thing. So you might ask, well, how do you even do error correction? How do you even detect during the computation, oh, I'm being swamped by errors, I better fix them or do something? That's what people are working on right now, error detection and error correction. I'll just say really quick, I know maybe this doesn't quite answer your question, but how do you even do that? Aren't you not allowed to observe the qubits until the very end? Well, here's what you do. You make what are some extra qubits, not the main ones that are doing the computation, but some extras. They're called ancilla qubits. That's the fancy word for extra. Got to be fancy. And you have the ancilla qubits store, using some quantum gates, some information about how well the computation is going on the other qubits. And you measure just those ones. You can do that in a quantum computer. You can say, I just want to measure that one, and that one, not all the rest. That's a thing. And from those ancilla qubits, you can say, oh, I've detected the following error syndrome, and then I can apply some quantum gates on the fly to the rest of the qubits to put them back where they're supposed to be. That's called error correction. So that is a path towards knowing something's going wrong, mid-circuit, by the way. Something's going wrong and I'm gonna end up with the wrong card. I need to correct it. But that's the huge area of research called error correction. Massive. Thousands of brilliant minds and gazillions of dollars are going into just error correction. Does that help?
Yes, thank you.
Thank you.
All right, real quick, I have a favor for everybody. Was that great or what? Yeah, very phenomenal. We enjoy doing stuff like this. We enjoy having pizza for you, but the school really needs to see and hear from you if you enjoy events like this. And so we would really appreciate it if you'd take that terabyte device that you have in your pocket and scan the QR code and fill out a survey. Fill this out, let us know, well, answer the questions on the survey to let us and other administrators at the school know what you thought about this event. So we really appreciate that. Also, I would encourage you, if you were curious about something and just a little too shy to ask, my guess is Dr. Brown will stick around for 10 or 15 minutes here and give you a chance to kind of ask him a few more questions. I also would encourage you, of course, like Dr. Brown said, there's tons of information available on Google and YouTube, but our library has come and brought some examples of some of the materials they have that are applicable to this topic. So I would encourage you to stop by the table. They have everything here. The books that are on the table, if one of them looks interesting, I think you can check it out tonight and take it home with you. So that's pretty cool. So stop by. He also has links to digital resources that you can grab as well. So be sure and check that out on your way out. And then don't forget to do the survey. And then Catalina has one more thing.
We all appreciate Dr. Brown coming to speak about quantum computers, and we want to give him a little token of our appreciation for our speaker, STEM guest. Okay, this wraps up our event for tonight, and hopefully you can make up for our next semester events, which will have about 2 next semester and 2 during the following semester as well. And thank you for coming, and have a great day this evening.